Hello, today we'll be solving this problem called sum of divisors. So let sigma of n denote the sum of divisors of an integer n. For example, sigma of 12 would be equal to 1 plus 2 plus 3 plus 4 plus 6 plus 12 for a total of 28. Our task is to calculate the sum from I equals 1 up to n of sigma of I, and this modulo 8,000,007. And notice here n can be very large, up to 10 to the 12th. And for example, for n equals 5, we would compute sigma of 1 plus sigma of 2 up to sigma of 5, and this will give us a total of 21. So let's go to the drawing board and see how we could come up with an answer. So as we saw in the example, the sum of sigmas from I equals 1 up to 5 is equal to 21. So let's go ahead and work this example out to make sure that's correct. So let's go ahead and list the divisors of all i's from 1 to 5. So for 1 we only have 1, for 2 we have 1 and 2, for 3 we would have 1 and 3, for 4 we have 1, 2 and 4, and finally for 5 we have 1 and 5. And if we add all this up, so here we have 5 ones, so 5 plus 5, that's 10, plus 5 again, that's 15, and plus 6, that would give us a grand total of 21. So now let's get a better intuition about this problem by listing the divisors of numbers up to 12. So we will get the following. So these are the divisors of all numbers from 1 to 12. And looking at this, we immediately know that the naive approach or the straightforward approach of looping through all values from 1 up to n and listing the divisors, then adding them up is not optimal because we immediately see that we can do something better. So here, if we look through all the numbers from 1 to n, we would have a complexity of O of n. Then in order to list the divisors here, we would require square root of n. So the total complexity here would be O of n times square root of n. And instead we can see here that there are patterns that emerge from this list. For example, all numbers have 1 as their divisors. And for 2, it does that jump that we are getting used to see now. So it skips 1 and gets 1. Basically all multiples of 2. And the same goes on for 3. It makes a jump of 3. And so on. So basically, after we list all the divisors, we're gonna accumulate all these numbers together. So we only need to know the number of occurrences of ones, twos, and so on. And if I ask you how many ones would be here, the answer here is 12. And why did we get 12? Simply because 12 divided by 1 is equal to 12. And for 2 we have 1, 2, 3, 4, 5, 6 twos. And why did we get 6? Because 12 divided by 2 is equal to 6. And for 3 we have 1, 2, 3, 4. So 12 divided by 3 is indeed equal to 4. And this works also for numbers that are not divisors of 12. For example, we see that we have a 5 here and a 5 here. And if we went ahead and divided 12 by 5, we would get 2 indeed. So we can see right from here that the number of occurrences of all values up to n will be just that number divided, or rather n divided by that number. So this gives us an algorithm that would work in all of n, and we will just look for all values from I equals 1 up to I less than or equal to n, and we will just add to our answer n divided by I times I. So basically here we have 6 occurrences of 2, and each one of them will contribute a 2 to the answer. So the contributions of 2 will be just 12 divided by 2, which is 6, times 2, which is 12. And indeed, if we went ahead and added these numbers together, we'll get 2 plus 4 plus 6 plus 8 plus 10, and that would give us 12. So this algorithm is better than this one in the sense that we don't have to compute the divisors for all numbers, but it is still not optimal because as we know n can be as large as 10 to the 12th, and our threshold is only up to 10 to the 8th. So we need to improve our algorithm. And in order to do that, let me go ahead and work out this example for 12 again. So let's continue. I went ahead and listed all the numbers from 1 to 12, and for each number I calculated the value 12 divided by I. And by this, of course, I mean the division in computer programming that is rounded down. So 12 divided by 1 is 12, and so on. And as you can see here, these values form blocks. So this is 12, this is 6, 4, 3. Then we have a block of 2's, then a block of 1. So in our O of n approach, we would go ahead and compute the answer for all these values separately. So it seems like we would improve our complexity if we were able to uh, process all these values together. But maybe that won't be enough as well, because maybe this block of 1 contains these 6 values, but it's not gonna help us much because maybe maybe we're gonna have n over 2 blocks, and each block will contain 2 numbers, for example. But this still will be asymptotic to O over n, even if this is n divided by 2. So let's actually go ahead and find out the number of distinct values we would have here, like the number of values we'd have in this bottom part of this chart. So to reiterate what I just said, I have a I that belongs to the range 1n, and I want to know the number of distinct values of n divided by I. And in order to answer this question, I will break down my interval to two parts. The first part is from 1 to square root of n, and the second part is gonna be from square root of n plus 1 up to n. So in this first part, even if n over I for all i's belonging to this interval are distinct, I only have square root of n values for I. So even if they are all distinct, n over I will only have square root of n distinct values. And if I belongs to this interval, then n over I is gonna be smaller than or equal to square root of n, because I is larger than square root of n plus 1, and therefore we also gonna have only square root of n distinct values, for a total of 2 times square root of n distinct values. So therefore I'm gonna have at most 2 times square root of n buckets here, or as I call them, blocks. So if we were able to compute the answer for each block efficiently, then we would be able to reduce our complexity to O of square root of n times whatever time we would require to compute the value for each block. So now the first thing we need to do is finding a way of determining these blocks, or in other words, finding a way of finding the boundaries of each block. So we'll start with I equals 1, and in this case we'll get a quotient that is equal to 12 divided by 1, which is equal to 12. And we want to know what is the next value here that will give us a quotient that is different from 12. So we got this q by dividing 12 by I. Therefore, I is equal to 12 divided by q. And since we want to get the next value, the smallest next value that is different from, that would give us a quotient that is different from this q, we can just pick I prime to be equal to 12 over k plus 1. And this will actually give us the immediate next value of q. And in this case, if we calculate this, we will get 12 over 12 plus 1, which is 2. So our next value will be I is equal to 2. And this will give us a quotient that is equal to 12 over 2. And this would be equal to 6. And our next value I prime will be equal to 12 over 6 plus 1, and this will give us 3. So our next value I will be equal to 3, and it will give us a quotient that is equal to 12 over 3, which is equal to 4. And our next value I prime will be equal to 12 over 4 plus 1, which is gonna give us 4. So we're gonna jump to the next value I, that is equal to 4, and this will give us a quotient that is equal to 12 over 4, which is equal to 3. And this will give us the next value I prime, that is equal to 12 divided by 3 plus 1, which is equal to 5. So our next value I is equal to 5, and it's gonna give us a quotient that is equal to 12 divided by 5, which is equal to 2. But notice what's gonna happen now. If this works, we need to jump. Our next value of I needs to be 7, because this 6 has the same quotient as 5. So let's check if that works. So I prime will be equal to 12 divided by 2 plus 1. So 6 plus 1 is indeed equal to 7. So we immediately gonna jump to the end of this block, which is gonna be, or to the beginning of the next block, which is gonna be 7. And 7 is going to give us a quotient of 12 divided by 7, which is equal to 1. And our next value I prime will be equal to 12 divided by 1 plus 1, which is equal to 13. And since 13 is larger than our 12, we will just stop here. And this way, as you saw, we were able to jump from each block to the beginning of the next block. So we jumped from 3 to 5, then from 5 to 7. And that's ideal, because now we only gonna jump through square root of n blocks, and we do that in all of one. So our complexity so far is square root of n times whatever complexity we will need to compute the sum of all these values. Because remember, we are trying to calculate the sum of divisors. So we know that 7 is gonna contribute only once as a divisor, but we don't actually count the number of contributions, but we actually count the sum of divisors. So we need to add 7 plus 8 plus 9 plus 10 plus 11 plus 12. And this comes in handy because our block is continuous, and as we saw from previous problems, we know how to calculate the sum from 1 up to some value n. And what we need to do now is to extend this to calculate the sum from some value a to some value b. And we actually can do this really easily, because this is just the sum from 1 to b minus the sum from 1 to a minus 1. And as a reminder, we know that the sum from 1 to n is equal to n times n plus 1 over 2. So here for each block we know its beginning and its end. So basically this first block is gonna start from 1 and it's gonna end at 2. So 2 is not included. So here we will need to calculate the sum from 1 to 2, and it's just gonna give us 1. So actually we're gonna multiply this 12 by 1. And then here we're gonna calculate the sum from 2 to 3 not included, so from 2 to 2, and it's gonna give us 2. So that's why we multiply this by 2. Then for this we're gonna calculate the sum from 3 to 4, and since it's not included, it's just gonna be 3, so this is gonna be multiplied times 3. The same here, so the sum from 4 to 5 is just gonna be 4 because 5 is not included, so this is gonna be times 4. And then here notice we have two values, so from 5 to 7 actually we need to sum 5 plus 6 for a total of 11, and that's why we will multiply this by 11. And we could get 11 by summing the values, like the values from 1 to 6. This is gonna give us 6 times 7 over 2, which is 21, minus the sum from 1 to 4, which is gonna give us 4 times 5 over 2, for a sum of 10. So 21 minus 10 is indeed equal to 11. And finally, as we said here, we're gonna calculate the sum from 7 up to the end, which is 12. So the sum here can be computed the same way. We could do 12 times 13 divided by 2, and that's gonna give us 12 times 13 divided by 2, so 78, I guess. So 60 plus 18 is 78, minus 6 times 7 divided by 2 is 21, for a total of 57. So this will be multiplied by 57, and at the end we will just sum this. But notice here there is an issue here. We are computing the sum modulo our prime number a billion and 7, and this will be problematic because in order to calculate the sum of a range we actually divide by 2. And here we need to warn against a misconception that many have, and that is that I divided by b modulo sum prime is actually equal to a modulo p over b modulo p, and this is wrong. The modulo can be distributed over multiplication, so a times b modulo p is equal to a mod p times b mod p. So that's correct. However, the division here is not valid. We cannot just divide by that. But luckily, as we saw in previous problems, we know that a raised to the p minus 1 is congruent to 1 mod p. And we got this thanks to Fermat's little theorem. And we could use this in order to simplify our issue here. So we could use this to find what's called the modular inverse of a number. And in order to compute that, we just raise the number to the p minus 2 power. And let's see why that works. So my claim here is that a over b modulo p is actually equal to a mod p times b raised to the p minus second power mod p. And in order to prove that, I will just multiply the top and bottom by a b raised to the p minus second power. So a over b mod p is equal to a times b raised to the p minus second power over b times b raised to the p minus second power. So this will be equal to a times b raised to the p minus second power over b raised to the p minus first power. And as we saw, thanks to Fermat's little theorem, this is just 1. So this will be equal to a times b raised to the p minus second power. So in other words, if you have a division here and you want to bring it to the top, you just take whatever is here, raise it to the p minus second power, and actually use it right away in multiplication. And that's precisely what we're gonna do here. So instead of dividing by 2, we're gonna multiply by 2 raised to the p minus second power. And as you can see here, we're gonna use our binary exponentiation again. So it is a tool that we're gonna use over and over again. Now let's check out our code. So this is our program. As I said, the modular binary exponentiation is gonna be so useful that we're just gonna add it to our template. And I invite you to watch the video about it if you've missed it. And in this program, we're just gonna start by reading our n. And notice here that we have to use long longs because it can be up to 10 to the 12th. Then I'm just gonna declare my answer and initialize it with 0. Then I'm gonna loop through the blocks. As we saw, we're gonna start with I equals 1, and I'm also gonna declare this j, which is gonna represent the beginning of the next block. And I will keep going as long as I is less than or equal to n. And each time the beginning of this block will be switched with the beginning of the next block. That's why I set I is equal to j. So to start with, I'll calculate my quotient, which is just equal to n over I. And as we saw, the beginning of the next block is gonna be equal to n divided by q plus 1. So what I need to calculate now is the sum of values in the blocks. So like in this example, I need to calculate the sum of these values. So I'm gonna calculate the sum of values from 1 to 12. Then I'm gonna subtract that by the sum of values from 1 to 6. So as I said, I need to calculate the range sum up to j minus 1, because remember j is the beginning of the next block, so I'll have to stop at j minus 1, and this is gonna be equal to j times j minus 1. And here I need to take mod because j can be larger than my mod, and if it is larger than say 10 to the 10th, if I multiply it by itself, it's gonna be larger than max of long. So that's why I'm taking mod here and mod here. So the sum up to j minus 1 is gonna be equal to j minus 1 times j divided by 2. And since we said that we cannot divide by 2 with respect to a modulo, I'm gonna actually multiply by 2 raised to the mod minus 2. And I will do the same thing for the range sum up to I minus 1, because remember I minus 1 is also not included in my range. My range is from I to j minus 1. So similarly, this will be equal to I times I minus 1 divided by 2, and which is equivalent to multiplying by 2 raised to mod minus 2. So this is gonna be the sum of all values in my blocks like this, and I need to multiply this sum by the quotient that represents this block, like in this case 1. So that's what I'm gonna do here. So first I'm gonna compute the sum of this range, like, which is gonna be just the difference between the two. And notice here what I did. Whenever we are calculating some value modulo and there is a difference here, we always need to add a mod here. And the reason why we need to do that is, for example, we know that this sum is gonna be larger than this sum, but maybe when we took the modulo, this sum became smaller than this one. And when we take the difference, all this is gonna be a negative number. And our answer needs to always be between 0 and mod minus 1. But if we just leave it like that, it's gonna be a negative number and it's not gonna be between 0 and mod minus 1. And that's precisely why we add mod to it, so it becomes in the range 0 mod minus 1. And then we just perform the mod again. And now that we've calculated the sum of all the range sum that have a quotient equal to q, we will just add that to our answer. So we will update our answer by q, and I take its mod times the range with quotient q, and this will just update the answer, and at the end I'll just print my answer. So that's pretty much it. Let's go ahead and submit. So that worked. Thank you for watching. See you in the next video. Bye bye.